Hello students, today we are starting with our physics lecture. Earlier up to 8th class you are having general science, but from 9th onward the general science is distributed in 3: physics, chemistry and bio. In physics we are having chapters 8, 9, 10, 11 and 12. So this is your first lecture of physics. We are starting with chapter 8. The name of the chapter is motion. Now students, see the book, pause the video, take the book and see the book. The chapter is motion. So as you are sitting in a chair, that means you are in the rest position. Rest and motion, these are two states of motion. How to define rest? Rest, when the objects which do not change its position with time, the objects which do not change its position with time, they are said to be in rest. You are sitting in a chair, that means you are at rest. You can see this blackboard. This blackboard is its own position. It is not changing its position though the time is passing. So this blackboard is also at rest. A car which is parked in front of your house, it is also at rest. So rest means when the object is not changing its position though the time is going on, though the time is changing. Now let us see what is motion. Motion means the object is said to be in motion when object changes its position with time. Object changes its position with time. Then the object is said to be in motion. Take an example, a bird is flying in the sky. When the birds are flying in the sky, they are changing their position with time. Or the vehicles which are running on the road. Next example, you can say when the blades of the fan, they are moving. These all are examples of objects which are in motion. Can you give any example of the motion? Yes. Motion and rest, they are relative terms. Motion and rest, they are relative terms. What does relative term means? An object may appear to be moving for one person and it may appear stationary for the another person. Take an example of a moving train. When a train is moving, then the passengers which are standing on the platform, they are saying that the person who is sitting in the train is in motion. Person who is sitting in the train is in motion. But the passengers which are in train, they look at each other and they say that they are at rest. They are at rest. So, motion and rest are relative terms. One more example, moving bus. Take an example of moving bus. A bus is moving. A person who is standing on a road can say that the passenger sitting in the bus is moving. But the other passenger who is in the bus feels that all the passengers in the bus are at rest. So in these two examples of moving train, moving bus, you can see that the person appears stationary to someone and it appears moving to some another. So they are relative terms. Object may appear to be moving for one person and stationary for some another. So what is our conclusion? An object is in motion with respect to one reference point, but it may be at rest with respect to another reference point. Again we will see the example of a bus. The bus is moving and the person who is standing on the road we are taking as one reference point. According to him, the passengers in the bus are moving. Now take another reference point. Another passenger in the bus feels that all other passengers are at rest. So as we change the reference point, the term rest and motion also changes. We will see what are the types of motion. The first is linear motion. When the objects move in a straight line path, then the motion is linear motion. Examples: a car moving on a straight road, or if you drop a ball from some height. These two are examples of linear motion. Second one, circular motion. Objects move in a circular path about a fixed point. Objects move in a circular path about a fixed point. Examples: merry-go-round, fan, these spinning top. These are examples of circular motion. Third one, it is vibratory motion. Vibratory motion, the objects move to and fro about a mean position. To and fro about mean position. To and fro means forward and backward about mean position. Then it is called vibratory motion. Examples of vibratory motion are a child on a swing, swinging on a swing. Another example, simple pendulum, which moves to and fro about its mean position. Now students, open page number 98. See the activity 8.1. In activity 8.1, a question is asked whether the walls of your classroom are at rest or in motion. Now you are sitting at home, so the question we will change, a small change we will do there. Whether the walls of your room where you are sitting and watching this video are at rest or in motion. Now observe your walls. Are they changing the position with time? No. So the walls are at rest. The walls are at rest with reference to your house, with reference to you. But if someone is standing on the moon and he is watching to your house, then the house is situated on the earth. The person who is standing on the moon, for him the earth is in motion. So your house is also in motion and the walls of your room are also in motion. So this is a nice example which tells us that rest and motion are relative terms. Second activity 8.2. Have you ever experienced that the train in which you are sitting appears to move while it is at rest? I am repeating the question. The train is at rest, you are sitting in it, but have you experienced that the train appears to move? Yes, it occurs, it happens. When the train is at rest, when you are sitting in it, but by that time, if another train moves which is parallel with your train with a fast speed, then it feels that, it appears that your train is also in motion. Now we are going to see the activity 8.3. In this activity 8.3, here they have given the motion around the object. The motions which are uncontrolled, which are erratic, like flooded river, hurricane, tsunami, these are uncontrolled motions. We cannot control them. But some controlled motions are also there, such as generation of hydroelectric power or applying brake to the car, these are controlled motions. Here they are asking the question, is it necessity to study the erratic motions, erratic uncontrolled motions of some objects and learn to control them? Now the answer is yes, we want to learn the erratic motion, uncontrolled motion, and we want to learn how to control them, so it will be helpful to the humans. It will be helpful to our mankind. So we want to study the uncontrolled motions also. Next we are going to discuss how to describe a motion. Let us see how to describe the position of an object. Describing position of object, or you can say describing location of object. To describe the position of object, we need to specify reference point, and reference point is called as origin. To understand this, we take an example. Suppose someone asks you what is the address of your school or where is your school, then you may say that our school is 2 km in southeast direction from RR Cat. So here in this example, you have taken RR Cat as a reference point. This reference point is called as a origin. You can take another reference point also, but here in this example we have taken reference point as RR Cat, and this will act as an origin while describing the address of our school. Now we are describing the motion of an object along a straight line. For this we have taken an object which is moving along a straight line, and here O is a reference point or the origin. A, B and C, these are the different position of the object at different instant of time. When the object moves from O to C to B and reaches A and returns back again to C through B. First the object goes from O to A, so the distance covered from O to A, it is equal to 60. It returns back and reaches C through B. So the distance AC, it is 35. We want to find out what is the distance covered by the object in this. The distance covered is equal to the total path length the object has covered from O to A and from A to C. That is equal to OA plus AC. That is 60 plus 35, and it is equal to 95 km. For finding out the distance, we are finding the total path length, actual path length covered by the object. Here direction of the path or the direction in which the object is moving we are not considering. Only we are considering the path length, and it is given by numerical value 95, which is magnitude, and here we can say a physical quantity which do not need direction for its complete description. It is called as a scalar quantity. In describing the distance travelled by object, we are not using the direction, but only we are using the actual path covered by the object. So we can say distance is a scalar quantity. Distance is a scalar quantity, and we are getting it is equal to 95 km. In the same example, if we want to find out displacement, in finding displacement we have to see what is the initial point and what is the final point where the object reaches. Initial point is O, our reference point. Final point is C, at which the object reaches finally. Here, for finding the displacement, we are finding out the shortest distance traveled by the object, and the shortest distance is OC. So displacement will become 25. What is the displacement? 25. Now we can see how we got this answer. We got this answer by keeping in mind the direction. When the object is going from O to A, it is in the forward direction, which we are taking as positive. So displacement, while finding displacement, we will write it is plus 60 because it goes in the forward direction. Then it returns back from A up to C. From A up to C. As it returns back, the direction is reverse. So the direction is backward. So we are taking negative sign. 60 minus 35. We are getting 25 kilometer. So you can see the difference between distance and displacement. Distance is 95. Displacement is 25. So the physical quantities which need the direction for their complete description as well as the magnitude, then they are called as vector quantities. Displacement is a vector quantity. The magnitude of distance 95 is not equal to the displacement. Is not equal to the displacement. Now we are discussing second example. The object moves from O to C, then B, and reaches at A, and again return back to B. Where it is returning back? It is returning back to B. Now we want to find out distance traveled. And as I said, distance traveled equal to total path length. Distance traveled is total path length. So from O to A, from O to A, how much it is? 60. From O to A it is 60. But it is again coming back to B. Again coming back to B. So what is the distance covered? 5, 10, 15, 20, 25. So 60 plus 25, we are getting 85 kilometer. We are getting 85 kilometer. Now we want to find out the displacement. We want to find out displacement when the object is going from O to A and returning back to B. Returning back to B. When it is going from O to A and returning back to B, its final position is B. And what is its initial position? O. Initial position is O. And displacement, as we said, it is the shortest distance between final and initial. Between final position and initial position. So displacement equal to final position minus initial. What is the final position? 35. What was initial? O, that is 0, our reference point. So 35 minus 0 equal to 35 kilometer. In finding out the displacement, we have taken the use of direction also. We have taken the use of direction also. Here, so we learned about two physical quantities. One is called distance and other is called as displacement. These two physical quantities are required to describe the motion of an object in a straight line. Distance is a scalar quantity and displacement is a vector quantity. Why displacement is vector quantity? Because for the complete description of displacement, we are using magnitude as well as direction. Magnitude as well as direction. So displacement is a vector quantity. How we use the magnitude as well as direction? See the same example. We are going in forward direction from O to A, so it is plus 60. But when we are returning back, we are going in backward direction. So from A to B, when we are coming, we have to subtract we have to subtract that returning back distance, which was 25. 60 minus 25, we got 35. Displacement, the magnitude of displacement is not equal to the distance. Magnitude means a numerical number, numerical value, number, and this magnitude of displacement is not equal to the distance traveled by an object. Now we are going to see the next example. Now I am taking one more example. In this example, a person is walking around a rectangular field. He is walking from A, reaches to B, and from B he reaches to C. So the person is going from A to B and B to C. A is our initial reference point, so it is taken as a origin. From A he reaches to C. Now we want to find out what is the distance covered by the person in going from A to B and B to C. As you see, the distance is AB plus BC. It will be 6 plus 8 and it is equal to 14 km. These 6 and 8 are in kilometer. Now I want to find out what is the displacement. The displacement is shortest distance between final and initial. Between final and initial, so this AC displacement is equal to AC. Displacement is equal to AC. And what is the value of AC? By Pythagoras theorem, you can find out the value of AC, and that AC equal to 10 km. AC equal to 10 km. So in this example, you can see that the distance and displacement, they may not be equal to each other. The distance traveled from A to B, B to C, it is 14 km, but the displacement is 10 km, because displacement is the shortest distance traveled by the object between initial and final position. So it is equal to AC and AC equal to